Let me begin. Today's presentation is titled Microservice Dashboard Introduction and Deep Dive, presented by Merpay's Uekusa. In this session, I will introduce the dashboard we are developing for microservices. I would like to share with you how the microservice dashboard solves issues that have emerged in the course of operating microservices and the functions and mechanisms used to solve them. Thank you for your attention. First of all, let me briefly introduce myself. My name is Uekusa, and I'm a member of the Engineering Productivity team. As for my background, I joined Merpay in January 2018 and was involved in the development of several microservices as tech lead. I moved to the architect team and was involved in the development of the API gateway and the dashboard for the microservices I am going to talk about. I continue to work on the development of microservices dashboard in the engineering productive team, which separated from the architect team in January of this year. So, here is what I will discuss today. First, what is a microservice dashboard? I'd like to briefly introduce how we came to develop this service. Next, I'd like to focus on 5 of the features, technology stacks, and architectures we use in our microservices dashboard and explain how they work in detail. Finally, in the secondary use of data through APIs, I will introduce the APIs provided by microservice dashboard and actual use cases. Let me first tell you what a microservice dashboard is and the background behind its development. In a nutshell, the microservice dashboard is an in-house service that aims to collect and visualize information on all microservices. Anyone with an employee account can easily access and browse the microservice information. We also provide the collected data via API so that it can be utilized by other systems. I will provide more details on actual API use cases later. As Merpay grew, it became increasingly difficult to keep track of information on each microservice while they were being operated. For example, when you want to know the overview of a service, what SLOs are defined, and the team members developing the service, the Slack channel to talk about the service, and the pager duty settings for on-call, it was a big task since you need to check them one by one. To make tracking such information as easy as possible, we had been compiling each of the microservice information into an internal wiki as an operational document. But as Merpay's development scale grew, it became difficult to cover all services and keep updating the information. Therefore, we eliminated managing this operational dashboard and started developing the dashboard around December 2019 with the goal of easily tracking microservice information. In this section, we would like to introduce the functions and structure of the microservice dashboard in detail. These are the technology stacks we are using. The backend is implemented in Go. We use Cloud Spanner, PubSub, and Scheduler for GCP services. APIs are GraphQL and gRPC. The front-end is implemented in TypeScript. We use React for the front-end and Material UI for the UI tools. Data for display is obtained from GraphQL. Next is the architecture of the microservice dashboard, which is a single-page application. To reduce operational cost, Go servers deliver front-end build files. Authentication for the web app uses Google OAuth, which allows any employee account to log in. There are also two APIs, gRPC and GraphQL. gRPC is available to receive Cloud PubSub and scheduler requests. The request comes in the form of an HTTP request, and the API gateway converts it to gRPC through a command mechanism. The GraphQL API is provided to allow other systems to utilize data. It is available using the credentials of the Google Service account. I will then discuss the functions and mechanisms of the microservice dashboard, focusing on these 5 features it has. To begin with, I will introduce the function of visualizing the features in the service. This is intended to make tracking microservice information easily. By providing an at-a-glance overview of the service, the team members developing it, and the Slack channels to talk about services, we hope to help developers understand not only their own service, but also other services. We also expect this is used as one of the onboarding materials for new team members. There are 2 main types of data that are collected to compile information on microservices. The first is the microservice starter kit. Merpay uses a tool called Microservice Starter Kit to build microservices. This tool is a Terraform module provided by the platform team that will automatically prepare the infrastructure resources needed for the initial construction of microservices. The starter kit defines an ID called a service ID that uniquely identifies a service, and the microservice dashboard uses that ID to summarize information. The second is microservice spec. Information in microservices include metadata that cannot be expressed by the starter kit alone, which declaratively manage infrastructure resources. To express such metadata, a definition called microservices specification is provided. Specifically, it is a YAML file called service.yaml, which can describe an overview of the service, links to Slack, channels, and documentation, and so on. The structure of the YAML file is defined in protobuf. By defining the structure with protobufs, input validation and message marshalling are made easier to handle mechanically. These starter kits and spec files are maintained in a GitHub repository, specifically called Microservices Terraform. The Microservices Terraform repository has become a mono-repository of Terraform files for over hundreds of microservices. Each service has its own directory, and the Terraform files and spec files, including the starter kit configuration, are located in a structure like this. Here is a diagram of how the microservice starter kit collects data. The starter kit data is obtained by git cloning the microservices Terraform repository and parsing the starter kit Terraform files. Acquired data is grouped by service ID and stored in a database. This process is triggered by the cloud scheduler and executed twice a day. Microservices spec files are linked via PubSub push distribution. Spec files are published from CI in the Microservices Terraform repository. The spec file is converted from YAML to JSON and from JSON to protobuf messages when publishing. By converting to a protobuf message, any undefined fields result in an error which can be noticed there. We also use a plugin called protocgen-validate to check input. When the microservice dashboard receives a PubSub message, it processes it into a more manageable form and stores it in the database. Basically, we publish messages triggered by file change, but we also publish all microservices spec files once a day in case they are missed. And here is a visualization of the collected microservice information. This service list shows all microservices and the teams, descriptions, and others associated with them. The data is also used for inventory microservices. This is the service overview screen. It contains information such as Slack links and documentations. So if you want to know basic information about microservices, this screen will give you the general idea. Information about the team is available through the Microservices Team Kit. Merpay uses a tool called Microservices Team Kit to manage the team. This tool, as well as the Starter Kit, is a Terraform module provided by the platform team that allows for declarative management of the team's member list and permissions to resources. You can tie the Team Kit from the Starter Kit, and the Microservice dashboard also ties the service to the team based on that information. The data for the Team Kit is collected using the same mechanism as the Starter Kit described earlier. Here is a screen visualizing the team's information collected. Team members are listed, and it is easy to see at a glance who is in which role. GitHub accounts and Slack mentions are also collected as data, which can be tracked on this screen. The ability to clearly identify the roles of each team member has made it easier to find out who the manager is when, for example, I need to consult with another team's manager. Next, I will cover the function to visualize the information assets of the services. The purpose of this function is to allow us to understand what information assets the microservices hold. By systematically managing the information assets held in microservices, we can streamline the inventory of information, and understanding the importance of the service will be useful in analyzing information security measures.
The information assets of the service are currently databased for personal information only. The classification of personal information is defined in protobuf and can be described in the spec file as metadata for the microservice. Each microservice owner is responsible for describing the information assets they manage in the spec file. The classification of personal information is defined by a matrix of personal information categories and types of personal information. The importance of the service, which is determined by the combination of the classification and type, is defined in the same way. For example, if there is a combination of a customer category and a credit card type of information, the level of information is top secret. Here is the visualization of the collected data. The top column shows the personal data category, and the left-hand row shows the type of personal data. In this example, the customer service credit information line is ticked, so you can see that the service has the customer's balance information, and so on. It is also possible to automatically generate an information asset ledger based on the data collected. The information asset ledger is a document that summarizes the information assets handled by a department in order to manage them properly. In the past, they had to manually manage this document on a spreadsheet, which was very difficult, but now they are able to automatically generate it from the data they have collected, which has led to significant efficiency gains. Now we talk about the feature to visualize service dependencies. This feature is intended to make it easier to understand the callers and the call destinations of microservices. It enables developers to notice if they are receiving requests from unknown services or if they know of requests to unintended services. The service dependencies are each graphs based on 3 different sets of data. The first is the Datadog Service Dependency API. Second is the network policy settings managed by the microservice Terraform repository. The third is the value set in the microservice environmental variable. We believe that the third data is most reliable, as almost all Merpay microservices set the destination of the request in the environmental variable. So today we will show you how to create a dependency graph based on the third environmental variable. Merpay microservice runs on Kubernetes. Kubernetes provides a mechanism called controller that performs arbitrary processing in response to changes in the state of a specific resource. Using this mechanism, we are developing a custom controller to retrieve microservice environment variables. Specifically, pods and cron jobs are specified as resources handled by the custom controller, and the reconciliation process acquires environment variables, including the config map in the namespace. From the retrieved environment variables, strings that apply to the destination pattern are extracted and stored in the database. Reconciling pod and cron job resources is quite numerous, so the queuing system is used to regulate the flow of processing. Another problem is that the memory usage is quite high. Here is a visualization of the data collected in this way. The service in the blue frame on the left is the caller, and the service in the red frame on the right is the destination. In this example, you can see how the Kozo Echo JP service is receiving requests from the Mercari and Merpay gateway services and making requests to the Mercari authority service. This is followed by a feature for visualizing the cost of services. This function is intended to help members of the organization to find services that can be cost optimized and for the development team to understand the status of a host of services. The information on the cost of services is based on data that the platform team aggregates into a big query every month. Currently, 3 types of costs are collected: GCP, GKE, and Datadog. Here is a diagram of the system for collecting information on the cost of services. Once a month, we execute a query to get the cost data in BigQuery, and the acquired data is grouped by service ID and stored in a database. Here is a screen visualizing the data collected this way. The monthly cost history is graphed for 6 months. Developers can look at this to see if there have been any changes in the cost status compared to the past. There's also a dashboard screen that summarizes the cost history for all microservices. This screen lists the cost history for each microservice. You can see the cost trends for all microservices for the past few months. Finally, I will talk about the feature that visualizes the quality of the service. This feature aims to give members of the organization as well as the development team an overview of the reliability of the microservice. The Merpay SRE team is leading the development of this feature. To visualize quality, we use the status of the microservice SLOs. At Merpay, the SRD team has put in place the infrastructure to support the configuration of microservice SLOs. A Terraform module called SLO module is provided to declaratively manage the SLO monitoring of Datadogs, for example. Here is a diagram of the mechanism for collecting SLO status. The SLO module file is placed in the microservice Terraform, and when a resource is created in Datadog, the ID of that resource is linked to the microservice dashboard in PubSub. The microservice dashboard uses the ID of that resource to retrieve the SLO status from the Datadog API once a day and store it in the database. Here is a visualization of the data collected in this way. It shows the SLO history of the microservice and the SLO status of each monitor. The history can be checked on a weekly, monthly, and quarterly basis, making it easy to see whether the SLO has been maintained for that period of time. We also have a dashboard screen that summarizes the SLO history of all microservices. This screen provides a list of whether SLOs have been maintained for each microservice. If any microservice is not maintaining its SLO, they will turn red, as shown in this screen, so that they can be easily identified. Finally, I will introduce the API provided by Microservice Dashboard and some examples of its use. Microservice Dashboard provides an API to make effective use of collected data within the company. By normalizing various types of data and making them reusable, they can be used conveniently when similar data is needed in different use cases. We also hope that this will promote the automation of operations and improve productivity. This API is not only available from the system, but also for individual users. The main reason for adopting GraphQL was that we simply wanted to try it out, but after actually using it, we feel that its flexibility, which is not bound by use cases, is a good match for the API in microservice dashboards, where it is impossible to predict how it will be used. Now, I will talk about two examples of actual use cases. The first is an example of individual use. Sometimes I ask microservices to respond to a request via Slack at here or other means, but some microservices don't seem to respond to my request. In such case, you can directly comment on the microservice owner and ask for support. But if there are multiple microservices like that, it can be difficult to find out where to comment. This is where the API is used to collect all of the comment destination at once. This is an example of using curl to extract data. The diagram shows how to obtain an ID token for authentication, pass the necessary queries as parameters, and make a request, and the data is returned as a result of the execution. This example shows a query to retrieve the mentions of all team members from the team resources associated with a service resource. This kind of data extraction is available to anyone with an internal account, as long as they follow the instructions and register to use the API. Second is an example of a systematic use of the system. Merpay uses a tool called Carrier for temporary authorization. Carrier is a tool developed by the platform team that allows users to request DCP or Kubernetes roles for a given service. When the service owner approves the request, a temporary authorization is granted. This is used when there is a need to work in production environment, for example. Carrier has an input form like the screen on the left. When the information required to make an authorization request is entered in this form, a notification is sent to the Slack channel of the specified service asking for approval of the request, as shown in the screen on the right. The API is used to check the service ID entered behind this process and to retrieve the Slack channel to be notified. The reason for this from the system is available by following the instructions to register a service account. I will summarize. Today, I introduced the microservice dashboard which we are developing. In order to collect and visualize information from all microservices, it is necessary to organize the information. In order to bring the information together, we need to put the information together. At Merpay, the declarative management of microservice information with regularity using infrastructure as a code, which is maintained by the platform team, was a great advantage in organizing the information. We will continue to manage the data we collect in a form that can be expressed as a code going forward. I also hope to continue expanding the use of API as part of our internal ecosystem. That concludes my presentation. Thank you very much for your attention.